A few days ago, the electric tractor was being used to do some rototilling, which is a task it was not designed to do, but was for some reason being used for. By me. Everything was going well when all of a sudden the tractor stopped driving forward and the rototiller stopped rototilling, but for some reason the motor kept spinning, which isn't really a feature the tractor is supposed to have, since there's no longer a clutch. The motor is just directly connected to the transmission, so unless I shift it into neutral, the motor shouldn't be able to spin without the wheels also spinning, and I didn't shift it into neutral, so something was definitely very wrong. If I run the motor, note that it's in gear right now, so it should be driving. Also, that's not the sound it normally makes. Let's take a look from the bottom. Well, that's not good. For context, when I converted this tractor to electric, I used a flexible coupling between the motor shaft and the transmission's input shaft. This coupling has 3 parts, with a flexible rubber thing in the middle called the spider. It's supposed to allow for slight misalignments between the 2 connected shafts. The transmission uses a spline shaft, so I cut apart the old clutch and stole the middle bit that has that spline pattern, and then I welded it to one side of the flexible coupling. Except, I'm not exactly the best welder in the world. I'm more like the second best, and I also may have used the absolute cheapest flexible coupling I could find on Amazon. So when the rototiller was being used and the motor was producing a lot of torque, the flexible coupler experienced a bit of an unplanned disassembly. In other words, it literally split in half. So after taking the motor off, we can see that not only did the weld fail, but the rubber spider disintegrated and 2 of the 3 teeth sheared right off from the coupling on the motor side. And by taking a closer look at where the part broke, it looks like it's made of cast iron. You can tell because of the way that it is. You can tell because the surface looks coarse, almost like stone, due to the cast iron having a random grain pattern. On the other hand, a machined or forged steel part would have a more linear grain pattern. A quick way to check if a piece of metal is steel or iron is with a spark test. Steel creates long, bright yellow sparks with lots of branches or forks. Cast iron, on the other hand, should create dull orange sparks in a short stream, with an overall small number of sparks. Sure enough, this does exactly that. Cast iron is notoriously difficult to weld, so it's no wonder the piece failed at the junction between the steel part and the iron part. So having said that, the proper way to fix this would be to get a new flexible coupling made from steel so that I can weld it to the splined part. Of course, you should know that I always do things the correct way, so that's exactly what I will be doing. No, I'm kidding, I just bought another cast iron one. As I always say, perfect is the enemy of ever getting anything done. Also, the steel ones are like 10 times the cost. This new one is, however, a lot larger than the old one, and I'm not just going to do a crappy little weld this time. I'm going to try and machine a press fit between the 2 parts. I don't like that. It seems like the bit that got welded is much harder than the rest of it, and it's throwing red hot bits of metal everywhere. If there are any machinists watching, please look away. Okay, I've machined this to be a press fit so it stays attached without any welding. However, I'm still gonna weld it just for good measure, and I've got a much more powerful welder this time. This part is all covered in oil, and I wasn't too interested in having it catch fire while I was welding, as this is something I already experienced the first time when I used a 3D printed alignment tool. So I dropped the part into my fancy new ultrasonic cleaner, which I got for Christmas, and allowed it to vibrate away for 10 minutes. Unfortunately, this didn't quite do the trick, and it still ended up catching on fire. I played around with the speeds and feeds, but it keeps making a bird's nest. This is just some used engine oil. I have no idea if this will actually make a difference. Well, all that did was make a bunch of smoke and send hot oil flying everywhere. Sometimes the intrusive thoughts win. This video is sponsored by JLC MC. You've probably heard of JLC PCB, but JLC MC is their related website that sells mechatronics components. If you're into building or repairing anything mechanical, it's a very useful resource. They carry a huge variety of parts with thousands of sizes and variants. I was really impressed with their prices and selection of pneumatic cylinders. There's thousands of them. They also sell consumables like solid carbide end mills, which I'll definitely be trying on my CNC setup. Most items ship in under a week, and a lot of the listings even include 3D CAD models that you can import right into your designs using Fusion, SolidWorks, or whatever CAD software you use. I personally hate when there's a specific part that I want to use, but I can't find the CAD model anywhere, so I have to model it myself, which is tedious and often results in a very crude approximation of the original part. So check out JLCMC using the link in the description, and now, back to work. With the new coupler ready, it was time for the fun task of removing the old broken one. For this, I had to use one of my least favorite tools, the puller. I always feel like these things require you to have 4 hands, one for each of the little arm thingies, and one to turn the wrench. Surprisingly, this actually went pretty smoothly and I got the new coupling installed in a few minutes. Next, it was time to put the coupler on the transmission input shaft. This is also quite difficult because there are 2 coaxial shafts and you have to make sure that they're clocked to the right positions relative to each other so that the coupler can slide onto both of them. I thought I could just wiggle it while tapping it with a mallet and eventually it would slide on, but that did not happen. I thought there might be a burr or some welding spatter, so I filed a small chamfer on the starting edge of the coupler, but it still wouldn't go on. Then I thought maybe there was some debris on the transmission shaft, so I brushed that off. And I discovered a cool phenomenon where I could just move the brush back and forth and it would automatically rotate the shaft each time to get all sides cleaned. Then I tried again to install the coupler and it finally went on. Then I awkwardly tried to put the motor back, but I discovered that the new coupler was slightly longer than the old one, so the hex spacers I made were now too long. I see a problem. The motor is already pressed up against the standoffs, but there's still a gap between the coupler, so like the motor needs to move more to the right, but the standoffs, they need to be shortened essentially, or I need to pull the coupler slightly off the motor shaft to the right. I ended up doing neither of those and just replacing the standoffs with a stack of washers. The crappy thing about cheap washers is that they're not consistent thicknesses, so I had to sort them into 4 groups and try to match the heights of the 4 groups to each other as closely as possible, which isn't just hard, it's NP hard. This is actually a well-studied problem in the field of computer science, and there are algorithms of varying degrees of complexity that can be used to solve it. Of course, I totally understand all of them. Unfortunately, I just don't have time to talk about them right now. With the washers ready, I could now actually install the motor. Check this out. A rare, holeless washer. I stole this. And after spending far too long elbow deep in the grimy orifice of this tractor, the motor was finally secure. Then I reattached the power cables to the motor and decided to reassess the way I originally mounted the motor controller. When I did this about a year ago, I secured it to the frame using duct tape, which I said at the time was just going to be a temporary measure, but we all know how that goes. It was now a year later, and after exposure to the elements, the duct tape had disintegrated, so I figured it was time to properly secure it. But not today. Today, I secured it with a single giant zip tie. But don't worry, it's just temporary. I'm always afraid that I'm going to decapitate myself backing out of this very low roofed shed. And I realized I don't even need to be in the seat. Much safer. A bunch of you pointed out that I accidentally installed this wheel backwards, which is noticeable when you compare the gap between the tire and this bit. But you see, I actually did this on purpose to increase the video engagement. But now I think it's finally time to fix this, so you'll have to find some other anomalies to comment on. I also discovered, rather alarmingly, that the nut on this throttle knob had come loose, so when I turned the knob, the entire potentiometer would just rotate. Not today. This took about 30 seconds to fix by adding a drop of Loctite and retightening the nut. Click. I think it would be really cool to add a solar roof to the tractor, because it spends a lot of time just sitting in the middle of a field doing nothing with the sun beating down on it. Rather than just letting the sun heat up the tractor, I may as well add some solar panels to trick the sun into recharging the battery. I found someone selling these 225 watt solar panels for $50 each, so I picked up 8 of them. They sure look a lot bigger in real life compared to the pictures I saw online, so I probably won't be able to fit all 8 of them on the tractor. A good rule of thumb when working out how much energy a solar panel will produce in a day is to multiply the wattage by 4 hours. So on a sunny day, each of these 225 watt solar panels should produce about 900 watt hours. The battery pack on the tractor is about 3.5 kilowatt hours, so it would take 4 of these panels to charge the tractor from 0 to 100% in one day. I made a crude 3D model of the tractor with the proper dimensions of its overall length and width, and it looks like I should be able to fit 4 panels on it pretty easily. Maybe I'll add some more that can fold out, but I want the tractor to have the same overall footprint as it currently does, so that it can fit through a garage door. I've also been trying to find a good solar charge controller, which has been tricky because this is a 72 volt battery. Most charge controllers are for 12 or 24 volt batteries, and I've seen a few for 48 volt systems, but hardly any work with 72 volt systems. I also want to be able to program the controller to stop charging at around 80% for the longevity of the battery. I found this one, which seems to be sold by a bunch of different brands. It's nice and small, it's simple to program, and it looks like it's probably waterproof, but it only handles up to 400 watts of solar input. So I would basically need one of these for each panel, which would be quite expensive and not the most elegant solution. So if you know of a good 72 volt charge controller that can handle at least 1800 watts of solar power, let me know in the comments. Also, I said I didn't want to put the original metal panels back on because I thought it looked cooler like this, but it's gotten to the point where real people in my life are telling me I should do it, so fine, you win. I'll do it, but I won't like it. If the solar roof thing sounds cool, make sure you subscribe so you don't miss it. And as always, big thanks to my patrons whose names are being shown on screen.